Recording is rolling. It is Tuesday, November 19th. So here's top scientists for energy, for my honors classes. So awesome job if you're on this list. I might use this recording for a few classes. So if they do, okay, here's my AP top scientists. They have their own quiz. Okay. And then my conceptual class, they have their own quiz, top scientists. So awesome job if you made the top scientist list. Top scientists, top scientists, top scientists. All right, you guys are doing good. Yeah. Okay, so for context here, there was an ASVAB assembly, periods 1 and 2. We're going to continue on our review. So we got a 2-day review between yesterday and today. Tomorrow, there's going to be, of course, this in-class quiz on, well, these topics. So projectiles, forces, Newton's laws, energy. So nothing to do with rotation, basically. And you guys can bring in 1 page of paper with notes on. If you want to do front and back, that's okay. Okay, front and back's okay. Just 1 page paper for any notes you guys have. All right, so you guys ready to be taking some notes here? Take some notes. All right, so I need to go back to yesterday. Figured out partway through class, I actually missed one of these posters. So let's just. All right, you guys remember drop a ball off a cliff? So the top of the cliff is 0.0, down is positive. Here's what distance fallen versus time looks like. Parabola. Speed versus time picks up at constant rate. Acceleration versus time, constant value. Looks like, okay. But one I was missing, I did realize this somehow got shuffled out of my deck. I realized this closer to the day yesterday was the table version of the same scenario. So same scenario, drop off a cliff. Right? So let me ask you guys, right after you release the ball, so you've just dropped it, how much is it accelerating? Yeah, 10 meters per second squared. Well, okay, it's really like 9.8, but I'm going to round it to 10 meters per second squared on Earth. Right? After 1 second, how much is it accelerating? 10 meters per second squared. After 2 seconds, how much? Yeah. Right. Guys, is it 10 meters per second squared all the way down? Yeah, as long as you ignore air drag, that'll be true. Right? Air drag would only slow it down, but if it's in a vacuum where air drag is negligible, that'll be true. Right? That's why this is a constant value graph. Right? It doesn't matter how much time it's falling for, it's always accelerating the same. Right? Now, acceleration, you guys know, is a rate change of velocity. So let's do the next column. Next column. So V, velocity. Now, guys, this word drop tells you the initial velocity is equal to what? Zero initial velocity. After 1 second, it's picked up to how fast? 10 meters per second. After 2 seconds, how fast? 20, 3 seconds. All right, is it picking up 10, 20, 30, 40, 50? Yeah. Okay, that's why, going back, okay, that's why velocity versus time looks linear, right? So it starts 0, 0, then 10, 20, 30, 40, 50. Boom, 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 boom. The slope is the gravity field, right? All right, you guys ready for the tricky column? Tricky column. How far has the ball fallen? And I do have to give you the first number. So I'll tell you the top of the cliff is 0.0, and we're just going to say how far has it fallen from there, right? All right, you guys ready for a question that's been tripping up students all day today? Okay. How far does the ball fall in 1 second? And don't say 10 meters. How far does it fall? 5 meters? Is that what you guys are saying? 5 meters? How'd you know it's 5 meters? Is that the college equation? H equals 1/2 gt squared? You guys remember Paul Hewitt going to my staff? He drops a rock, falls for, supposed to have been falling for 5 seconds. Gee, I wonder how deep it is. And how deep was it falling for 5 seconds? 5 and 5 is 125. Half of 10 is 5. It's about 125 meters deep. How'd you know that? College, isn't that? Except now we're just doing for 1 second. Guys, plug in 1 second, you're going to get 5 meters, right? 5 meters? That's this cell right here. Right? Plug in for 2 seconds, you get 20 meters. 3 seconds, you get 45 meters, right? 4 seconds, 80 meters, right? And if you plug in 5 seconds, how far do you get again? 125 meters. How'd you know that? College, that's right, college, 125 meters. That cliff is 125 meters tall. Right? Okay, you guys get that? All right, so that's a little bit fill in from yesterday. All right, and then let's get back on track though. All right, so yesterday, the last one you guys saw, right, the tail end of class, I flashed this one up and then the bell was ringing, and so that was the end of class right there. And so pick up from this point. I got a block on an incline. It's how many forces are acting on that block? 3. Yeah, I got the weight down. I got the normal force well, that's normal to the surface. That's why it's called the normal force, perpendicular surface. Okay? I got this friction force holding it in place to keep it in equilibrium. Now, guys, when you see equilibrium means the acceleration is equal to what? 0, which means the net force is equal to what? 0 meters per second squared, 0 newtons. Okay, which could be one of two different things. It might be at rest, or it might be moving. But if it is moving, it's constant velocity. Either of those is, well, oh, here's your conditions here: 0 net force and 0 acceleration. Right, could be either one of these stories. Okay. All right, so to make sense of this, I'm going to introduce a Cartesian system that runs parallel perpendicular to the surface. That's those dashed axes right there. Now the red and the blue vectors are already aligned to that system. That's all good. But this weight looks like its own angle relative to that axis system. This angle is this angle theta. So I need to break it into cosine and sine components. And when I do that, to go back to equilibrium, is this normal force exactly balancing out this mg cosine theta? Yep. And is this friction force exactly balancing out this mg sine theta? Yep, sure is too. Okay. Now, one more word on this breaking the weight into components. Notice I dashed the components, so I'm not double counting them. Okay. And we draw perpendicular to the surface and then parallel to the surface. You guys see this one down here? It's parallel to the surface, parallel. Is it drawn parallel to the ground like this? It's drawn parallel to the surface. Bing, 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 bing. You guys see that? Right? I'm really emphasizing that because guys, so many students over the years have a lot of trouble drawing parallel lines. Okay, so this is parallel to this. Okay, guys, that. Okay. All right, moving on. Next one, I'm just going to focus on this normal force as a function of that angle theta. Now, you guys just saw normal force is equivalent to mg cosine theta. We just talked about that. Okay, so what does this look like as you change theta? Here, 0 degrees, 30, 45, 60, 90 degrees. Okay? Now the weight's the same. That green weight, that's the same. Okay? You guys, look at the normal force. What's happening to the normal force? It's getting smaller. Because as this theta goes from 0 to 90 degrees, cosine of that angle gets smaller and smaller. Right? That's it. All right. Okay. All right. Let's change this up a little bit. Okay. I got rid of a force. Because which force did I just get rid of? Friction. Friction's gone. Okay. I still have a weight, which I broke into components. I still have this normal force, but that's all I have. This could be an air hockey puck on an air hockey table, but maybe I'm tilting the table, right? Or you know what else this could be? Do you guys remember one of the first labs I had you guys do was roll the Hot Wheels cars down the inclines? Okay. That could probably be really close to this also, couldn't it? It's really close. So a question you could get is like, what's the acceleration? Okay. So I would start with Newton's second law of motion. Okay. Now, in this case, guys, what is the net force acting on, say, that air hockey puck? What's the net force equal to? It's this component right here. It's the mg sine theta. Okay, just the sine component of the weight. So mg sine theta. So I'll substitute that right here because the cosine component cancels out with the normal force. Block's not accelerating this way. It's not accelerating this way. Okay, right. So mg sine theta. Now the mass of the block cancels, and here's the answer: g sine theta. So let's do a numerical example. Back when you guys were rolling cars down inclines, that was near the beginning of the class. That was way back. You guys were just kind of trying to figure out what acceleration even was at the time. Right. But now that you got this, we can revisit that question and say, hey, I wonder how much your cars were accelerating. Who remembers? What was this angle of the incline approximately? About 5 degrees? You guys remember it was about 5 degrees? So we get that 4, 5, 6 degrees, something like that. I'll call it 5 degrees. Right. So all I have to do is what can I plug in for G? 9.8 or 10 meters per second squared, and then sine, and then 5 degrees. Here's the answer: 0.85 meters per second squared. So let's say a little bit less than 1. Those Hot Wheels cars were accelerating a little bit less than 1 meter per second squared. I bet if you go back and you look at your lab data that you collected back in the day, it would be consistent with that. Right, you guys think? All right, I got one more incline poster for you guys. Now this one's a little more involved. Right, so the friction force is back. Right, I'm gonna shuffle this one at the end because it's a little bit more involved. This was a lab you guys did. And the lab question was, what's the coefficient of friction, say, between the block and the surface? And do you guys remember doing this? Some classes took textbooks and some classes took desks. It was kind of left up to you guys. And you tilted it until it broke friction and started sliding down. You guys remember doing that? Okay. And then based on this angle, you were able to figure out what was the coefficient of friction. Now I have a whole process here. I'm not going to go through it step by step, but just kind of flash to the end here. Here's the answer. It ends up being tangent of the angle, right? So if there is friction and it's sliding at constant velocity, that's an example of equilibrium. You know, the net force is 0, which really just goes back to this. So it's just a version of this all over again, right? What's the coefficient of friction? And there's the answer. It's just tangent of the angle. So, I remember I was going to do a specific application of this. I forget what class it was. It may have been you guys. You guys see this pulley system right here in front of me? Right now, if you're watching this video at home, I've got a ring stand. Right, there's like a horizontal bar going across, right, and then I've got some of these pulleys like on strings hanging from the horizontal bar. Except the horizontal bar going across, it's not exactly horizontal. It's more like tilted down a few degrees. But one of my classes, they mentioned, hey, those strings hanging from that not exactly horizontal bar, I bet there's got to be some friction. Otherwise, it just want to slide off. How much friction does there have to be? And the answer is right here. Here's the answer. And so all I had to do is take a protractor. Here's my protractor here. I'm going to take this off screen. I'm going to measure that angle right now. I'm going to hold it like this. Say, what is this angle right here? So let me do it. Right here in class. If you're in class, you can see it. It looks like it's about 14 degrees. It's about 14 degrees from the horizontal. So what I got to do, go up here, say what's tangent of 14 degrees. It's 0.25. So as long as the coefficient of friction between this string and this bar is more than 0.25, it's good. It's going to hold. And if it's less than 0.25, it's going to slip off. Right? But it's holding, so I know it's more than 1.25. Okay. Right, that's all. All right, you guys good with friction on an incline? All right. Yeah, here's a lab you guys did. All right. Maybe had you make a table or something. Great. Object hanging from a spring, maybe stretching the spring. So two forces, the weight's pulling down, the spring force is pulling up. Weight is mg, spring force is kx, as in F equals kx, that's Hooke's law, right? Guys, if you have any three of these, could you solve for the fourth? Okay, if I tell you the mass and the gravity field and how much it stretches x, could you solve for k, the spring constant in the spring? You guys do that, right? All right, you guys good there? So mg equals kx. That would be the next step, right? All right. Ooh, the chain gang. You guys ever played Barrel of Monkeys? You guys got all those little plastic monkeys all hanging like this. Right? You guys suppose you got a whole chain of monkeys. We need more monkeys. Would it be easier to be a monkey near the bottom hanging on, or a monkey near the top holding all your friends? Yeah, it'd be easier to be a monkey near the bottom. Right? You just gotta hold your own weight. The monkey near the top, it's gotta hold like all the monkeys. Right? Okay, so that tells you something about the tension in these springs. I bet it's most near the top, and it's less and less further down you go. There is a horizontal version of this question. It involves a train. If you ever get a physics question, there's a train. Choo choo. Suppose that engine is pulling all the carts behind it, and it's accelerating those carts. You think the front tension is the most because it's pulling all the carts? But by the time you get near the back, the last link just has to pull the caboose. You think it's probably the least tension? Yeah, there's not bad. All right. It's a version of that. Okay. Ooh, here's a lab I had you guys do. Just take a couple of spring scales and maybe hold them vertical and then change this angle. You guys were saying, how's the spring force change? Right here. Oh, here's a blown up picture. So same idea and the guiding principle how to solve this. Okay. So let's do some numbers. Suppose I hang on a 10 Newton weight. Here's 1 kilogram weighs 10 newtons. Guys, remember that? Hang out right here. Hang straight down. Okay. Now let's make these spring scales straight vertical to start off with. Guys, if it's 10 newtons down, what's the spring force rating in each scale? 5 and 5. Yeah, 5 and 5 up balances with the 10 down. That's okay, right? Then you start to spread it. Guys, as you spread it onto a Y shape, what happens to the spring force rating? Increases. It does. It gets more and more and more, right? Okay, so what's going on here? So here's your guiding principle, is that equilibrium, the force sums to 0. That's also true along each axis. So the sum of the forces in horizontally goes to 0. That's these two blue components here. So this one pulls right as much as this one pulls left. Okay? And the sum of the forces vertically also goes to 0. So this up and this up cancel with this down. So if this is 10 newtons down, do you think this is always 5 and 5? If it's symmetrical, yeah, it's always 5 and 5. Right? Which implies something else. Guys, can you ever make a perfect T shape? Can you ever pull these exactly horizontal? Can Arnold Schwarzenegger kind of go pull these exactly into a T shape? No, it's never going to happen because there's always 5 newtons and 5 newtons up. There's always some vertical component. So this 5 up and this 5 up cancels with this 10 down. That's what Screenwheel says right here. Right? The closer you make it to a T shape, what is the spring force approach? Infinity. Aha. Right, you guys good with that? Okay. This next one is just a layer deeper. So it's the same thing all over again. Same guiding principle. This pulls right as much as this pulls left. This up plus this up cancels with this down. Same thing, right? But what if it's asymmetrical? So I got two different angles. I got an alpha and a beta. That's okay. I can just break out sine and cosine. Right? So force right cosine beta, force left cosine alpha. That zeroes out right here. Right? Then force right sine beta, force left sine alpha. Add those together. That cancels out with mg down. That's this one right here. That's all it is. Right? You guys can solve that. That's force equilibrium in 2 dimensions, like a 2D puzzle. Guiding principle there. All right. I think if you guys get the guiding principle, I think you guys will be all right. All right, you guys good? All right. You guys remember building the Varinon frame? That was fun, trying to optimize the location to minimize transportation costs. Okay, got some factory out there. That was fun. All right. You guys remember Pythagoras cup? It's pretty fun too. All the water like siphoned out. So you had to figure out how that worked. Let's do a little trivia. I got a little extra time for some trivia here. Right? Because part of what makes this work is the fact that we're surrounded by some atmospheric pressure. Like this would not work in a vacuum. Right? You need some pressure to make this happen. Right? And because we're in a finite pressure, actually, how much pressure are we in? 1 atmosphere is equal to how many pascals? Great. Remind you guys what a pascal is. This 100 grams weighs, let's call it 1 Newton. It weighs pretty much 1 Newton. If I have a big old foam board that's 1 square meter, it's 1 meter by 1 meter, right? 1 meter stick by 1 meter stick, 1 meter by 1 meter, big old foam board. I set 1 Newton weight on it. 1 Newton on 1 square meter, that's 1 pascal of pressure, right? How many pascals of pressure are pushing on you right now? 101,000. You guys remember that from yesterday? 101,000 pascal. Okay. Right. Which means that there's a limit to like how long a straw you can use, how far you can pump up water. Like if I have a straw here, I'm like bloop, 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 pull up water out of a straw. I can only draw it so high. I can only make this Pythagoras cup so tall. So I'm driving down the interstate. I see a roadside attraction. The world's tallest Pythagoras cup. Well, that's cool. I want to check that out. How tall can you build a Pythagoras cup before it doesn't work anymore? Turns out 10.3 meters. Right. The amount of pressure running right now, by the way, that's approximately the width of this room, almost exactly. So the width of this room, if you filled it with water and turn it to the side, well, I guess it'd be easier to turn it to the side first, fill it with water. You dive all the way to the bottom. The amount of pressure you would feel at the bottom of that 10.3 meter deep swimming pool is equivalent to, say, what 1 atmosphere we're in right now. So I guess, it's sort of like 1 additional atmosphere of pressure compared to the vacuum of space. All right. Right. Elevator physics. Okay, that was a little trivia, but that's not gonna be on the quiz tomorrow. Elevator physics. Say I have an upward accelerating elevator, and I want to know what is my force reading on the scale. Right? What does the scale read? No, it's a normal force. Now I have 2 forces. I got a normal force up and a weight down that are unbalanced. Look, it's different forces because there's a net force so that you're accelerating. Okay? So what is that normal force equal to? Well, here's the derivation. So you can start off with, hey, is this Newton's second law of motion? Net force equals mass times acceleration, right? And the sum of forces, well, I got 2. So normal force up, weight down, subtract those, right? Substitute it right there, boom. Okay. So there's your net force, difference between the 2 forces, point, up, down, equals mass times acceleration, right? Do a little algebra shuffle, and boom, you got the reading on the scale. There's a normal force reading on the scale. Let's do a numerical example. Suppose you have a mass of 50 kilograms. So 50 kilograms, mass, right, 50 kilograms. Okay. Now, if you're standing out on the sidewalk, it's just mg would be your weight. You would weigh 500 newtons. You guys got that? 50 kilograms, weigh 500 newtons. Right. Right. Now you go into the elevator. Let's say the elevator is accelerating upward at 3 meters per second squared. You guys got that? 3 meters per second squared. Can I just do 10 plus 3 right here? All right, let's try that here. 10 plus 3, all times 50 kilograms. Now the scale rate's 650 newtons. Wow, you feel pretty heavy. Right? All right. Now that's upward accelerating. What if you're downward accelerating? Right. Here's all 3 basic scenarios. Here's upward accelerating. You guys just saw that. Right. Here's downward accelerating. And you can do a similar type derivation. The only thing that changes at the end is this plus changes to a minus. And the one in the middle is equilibrium, which could be a number of scenarios. You might be at rest, or you might be moving at constant velocity, maybe up, maybe down, maybe fast, maybe slow. But anything in equilibrium, if you're standing inside the elevator, you cannot distinguish the difference because they all feel identical. And scale rating is just exactly equal to your weight. Oh, one other little detail here. I did change this to a tension force, as in a tension in a cable pulling the elevator, but it's the exact same math. That's why it looks the same type of equation. Right? So that's a handy little equation, right? If you know how much the elevator is accelerating, either way, you can say either what's the tension in the cable or what's the scale rating. Something like that. All right. Ooh, all right. In elevator physics, that's going to lead nicely into a classic double elevator Atwood. All right, you guys remember Atwoods? You're going to see Atwoods right now, and then later in class today, you'll see Atwoods when we get to the energy section. A little bit different perspective. Okay. So the original lab you guys did with the Atwoods, the question I was asking was, what's the acceleration of the system as a function of the masses? You guys remember that? Okay. So let's see, how do you derive that through Newton's second law? Actually, that's just the pink box is Newton's second law of motion. There's Newton's second law. Net force over total mass. Right. Now, there's two different ways to approach this. And my preferred way is to go through what's called a whole system approach. I'll walk you guys through that first. So these two weights are competing clockwise versus counterclockwise, but they all kind of have to move together because they're all tied together with the same string. So, guys, from a whole system point of view, with clockwise versus counterclockwise, what would you say is the net force? This weight minus this weight, right? In fact, if they were the same weight, it would just zero out, wouldn't it? Right? So here's your net force, m2g minus m1g. Okay. And then the other question to fit into Newton's second law is, well, what's the total mass being moved? Wasn't that just m1 plus m2? Boom. There. So difference of weights over sum of masses. That's the acceleration for the classic double elevator Atwood. Right? You guys got classic Atwood? Okay. That's the answer. It's that gold box. Right. Now, sometimes you'll get a follow-up question that says, what's the tension in the string? To get the tension in the string, you have to either focus on only block 1 or only block 2. And then you can set up a different Newton's second law, but as it applies only to a single block. Right? And I did both of them down here. So I've got 2 green boxes. So here's the perspective of block 1, here's the perspective of block 2, and you can solve for the tension. Right, you guys got that? Right. Which actually leads me to the other way you could have set this up from the beginning. Let's say you solve this from scratch, right? You could have started with the 2 green boxes. Say, I'm going to set up an equation for the block 1, set up an equation for block 2, and solve this as a system of equations. And you can sort of simultaneously get the acceleration and the tension force in the string, right? In fact, a lot of textbooks and a lot of physics instructors prefer to do it that way. So if you take physics in college, some of you guys will, there's a good chance your college instructor might actually start with these 2 green boxes down here. But you still get the same gold box answer. The gold box is the actual answer, okay, for acceleration. Okay? Right, let me plant one more idea. Once you know the acceleration, you could go kinematic. So you could answer questions like, how far does it move after some time? How fast does it move after some time? How fast does it move after some distance moved? Right, those would be kinematic questions, right? Break out the kinematic form. Take out the kinematic form is right here. Once you know acceleration, you could handle any of these, right? Right. Now, I'm going to play that idea because later on when we get to energy, well, I'm going to cut that. Right, you guys good? Classic. Right. How about this modified version? So what if you guys also did this as a lab? So if you dig through your lab papers, but you find this too. So what if I have one weight hanging and I have another mass up here, but it's on this horizontal surface? And I see a bunch of forces, force, possible force, right? But really there's only one main force that matters that's driving the system to move. Guess which force is driving the system to move? The weight of the hanging block. This weight right here. And that's the one that matters. The tension force is just internal to the system, just holding it together, kind of like was on the last slide, right? And what about the weight of the surface block? Well, that's being canceled out by this normal force up here. In fact, if this is on little tiny wheels or a low friction system like you guys had, then this friction force would be negligible. So maybe you can just ignore it, right? So that's not even there. That cancels with that. Tension force is internal. The only force that really matters driving system is this M1G down here. So that is the net force. It's going to feed into Newton's second law. The total mass, the total inertia is the sum of the blocks, sum of the mass of the blocks. Right? There's the answer. The answer is that gold box right there. Right? Again, just like the last slide, if you want to answer the question, well, what is that tension force? Then you can either focus on just block 1 or block 2. I did both of them down here in these green boxes. Once you have the acceleration, you just pop that in there or there, and then solve for that tension. Boom, done. All right, that's how I would do it in class. Right? While you guys are finishing writing that, again, could have started with the green boxes. That could be your starting point, system of equations. You can sort of solve acceleration and tension at the same time, but the system of equations, you did that way too. Okay. Regardless of how you solve it, the answer is this gold box right here. Here's the acceleration. All right, you guys go with Atwoods. Atwoods. All right. We got all right, lab table. All right. Oh, I got a couple of bonus ones. Guys, if you're going around a curve, what force is acting as the centripetal force? The friction between the tires and the road. Right. I'm not going to ask about centripetal though, so that's a little bonus. Right. Here's another little bonus. There's a pendulum swinging. Right. Do you think the tension right here would be more than the weight? Versus if it was rest. If it was at rest, would the tension be equal to the weight? Yeah. But if it's swinging, you think the tension's more than the weight? Okay. Again, I'm not going to ask that tomorrow because that's a centripetal type question. Okay. Tension force minus weight equals mv squared over r. Right, good. Don't worry about that. That's not the question tomorrow. All right, energy time. You guys ready for some energy? So energy is measured in, guys, what does this J right here stand for? Joules. Okay. Now energy can take lots of different forms. Here's the main forms you care about. We're about to look at those also. And then one more concept. Guys, P, power, is measured in what? Watts. That's right. Watts. Now, careful, guys, this W and this W. This W up here as a variable stands for what? Work, and that's measured in joules. This W down here is a unit, that's watts. You guys just said that. And that's how you can quantify power. Okay, so different concepts, careful about that. So many letters. Okay? Don't worry about the blue lines yet. We're going to start that on Thursday. So, yeah. Okay. Okay, here's the main forms of mechanical energy you care about for this class. Okay. Now, energy can take a bunch of other forms too that are not on this page, like thermal energy we'll do next semester, like food energy, like calories. There's what else I want to say? Oh, like energy in a AA battery, like chemical energy. Right? None of those are here. So what are we working with? So work is force times distance. That's a dot product. That's a transfer of energy, really, is what that is. So if you transfer energy from one object to another, force times distance. Okay? Now, if you lift something for some height, I lift with mg. I lift a distance h. Hey, that's this next one right here. I give it potential energy, mgh. All right. So if I pick this up, put it on the shelf. I did some work lifting it, and I gave it mgh worth of potential energy sitting on the shelf. All right. This next one, the green box, is the universal form of potential energy. That is not going to show up in the quiz tomorrow. This one's a little bit more involved. If you send a rocket all the way to the moon, you say, well, this gravity field is changing. So, okay. But I'll show you guys later. This simplifies to this. Okay. So just focus on the gold boxes. Can you guys just focus on these 4 gold boxes? I think if you know the 4 gold boxes, you're going to be good for tomorrow. Okay. All right. So, spring potential energy. What's the energy in a spring? 1/2 kx squared. Now that's different from the force to compress a spring. Here, I have a spring right here. I see the spring right here in my ballpoint pen. I can press that. Guys, 2 questions. How much force does it take to compress that? F equals what? Kx. F equals Kx. Right? How much work did it take to compress the spring? 1/2 Kx squared. So F equals Kx. That's some number of newtons. Energy is 1/2 Kx squared. That's some number of joules. Different concept, right? All right. Last one you guys care about. Energy in motion, 1/2 mv squared. Something has a mass and a speed, right? Guys, energy. Is energy a scalar quantity or a vector quantity? Who says scalar? Who says scalar? Yeah, scalar. Right? Kind of like volume is a scalar. It doesn't have a direction that's associated with it, right? It's just an amount of something. You have a magnitude. You have more or less volume. right? But you have more or less energy, but it doesn't really have a direction. So this V right here, I'm going to call speed because it doesn't really matter if it's going up, right, left, down, 45 degrees. It doesn't matter the direction motion, just the fact that it's moving so fast. All right, so you guys go with forms of energy. Again, these 4 gold boxes, you guys are going to be good. All right, let's look at units. So 1 joule of energy. Guys, 1 joule of energy breaks it down to 1 what times what? Newtons times meters. Yeah, right. And if you forget that, just think about work equals force times distance. Force is in newtons, distance is in meters. Put it all together. Joule, Newton, meter. So if you push on something, 1 Newton for 1 meter, 1 Newton force for 1 meter, you did 1 joule of work pushing it. Newtons. Guess what does newtons break down into? Here's a hint. Think about Newton's second law of motion. F equals ma. What is mass measured in? Kilograms. What is acceleration measured in? Meters per second squared. Combine that with this meters here, put it all together. There's the answer. Kilogram meters squared per second squared. Okay. Guys, however many of these, can you create these or can you destroy these? No. However many of these there are in the universe right now, were there exactly the same number of these in the universe a billion years ago? Yep. And a billion years from now? Yep. Energy is conserved. You cannot create or destroy kilogram meters squared per second squared. Oh, that's interesting. Next one, power. So 1 watt. Because 1 watt is 1 watt per watt. 1 joule per second, like a rate of energy. So just say this is joules. So kilogram meters squared per second cubed. That's what 1 watt is. If you have a 20 watt light bulb, it's drawing 20 joules per second. You guys good with joules and watts? All right. Notice the base ingredients are kilograms, meters, and seconds. All right. Ooh, in physics, if you ever see a force versus displacement graph, force versus distance graph, you're probably going to get a question like how much work was done, how much energy was transferred, same question, right? And the answer is just the area under the curve. Now here I'm showing a constant force, so the area is very simply a rectangle, right? But on Hooke's law, I remember it was like a diagonal line, so it was more like a triangle shape. And what if you have some crazy Dr. Seuss curve, like is the work transferred? Just the area under the curve. That's all it is. If you can figure out whatever that is. All right, let's do some work examples. So work is force dot distance. Now that dot is a special kind of multiplication. It's called a dot product, which means you really only multiply together the parallel components. So if you have a force and a displacement that are off at different angles to each other, you only care about what's in the same direction, right? So example, let's say you lug something up the stairs, carry up the stairs. Right. Now I had to lift with a vertical type force, holding up the weight. It's pulling straight down. I have to pull straight up. Now the distance I moved is this weird diagonal type, right? But guys, was there any work carrying something across the room? No, because the force holding straight up and the direction motion going across are perpendicular. The dot product is equal to 0. This horizontal has nothing to do with the work input, right? But this vertical change does, because I had to carry it up the stairs. So it's d cosine theta, and then times the upward force, that's f d cosine theta, right? That's this, right? Now notice the angle I'm playing off is the angle between the force and the distance. That's not this angle down here. That's this angle up here, okay? If there was something really tricky, there's not going to be anything that's tricky tomorrow, but maybe in college, if they give you this angle down here, this is no longer cosine theta. It's now what? Sine theta? Okay, let me show that to you guys. So, you guys know about complementary angles? Okay, maybe you learned this in a math class. This is kind of an application here. Okay, complementary angles are angles that add up to what? 90 degrees? Okay. Okay. And if that's true, if alpha beta add up to 90 degrees, you can say this: sine of alpha equals cosine of beta. All right, try it out. You guys got a calculator. I bet if you do sine of 30 degrees and cosine of 60 degrees, I bet you get the same ratio. Yeah, you do. Right. Here's another way you can say it. Sine of alpha equals cosine of 90 minus alpha. Same thing. Okay. Right. So how does that apply to this? Well, if you were given this angle down here, suppose you got a really tricky question, they were trying to like throw a curveball at you guys, they gave you this angle. This would become sine of that angle. Or you could find this other complementary angle first. Really want to use the cosine. Okay? All right, pushing a shopping cart. Suppose you're pushing down and forward, but the shopping cart only moves forward. So the component of the force that really matters is F cosine theta. Again, notice I'm choosing this angle here between the force and the displacement, not this angle down here. Otherwise, this would flip from cosine to sine. So careful. But this is cosine, so it aligns with the formula. It's all good. Okay. So F cosine theta times D, shuffle around, Ft cosine theta, same thing. Right. All right. So you guys good with work? This force dot distance. All right. Force dot distance. Okay. All right. This one. So this one's more involved than anything I'll ask you tomorrow, but real fast, recap. Here's universal potential energy that always works. You have to use this for sending a rocket to the moon. And I can do a proof and show you guys that that simplifies to mgh at the surface of a planet. All right, so FYI, that's there. Kinetic energy is 1/2 mv squared. That's all you guys have to know. Kinetic energy is 1/2 mv squared. Here's kind of where it comes from. Two different perspectives. Okay, that's fine. All right, closed and open systems. So closed systems, if a system is closed, guys, how do you read this expression here? What does this say? The sum of energy initial equals the sum of energy final. That's conservation of energy. That's you cannot create or destroy energy. So if a system is closed, there's no external force acting on it, there's no work being done on it, right? Then however much energy is in the system is conserved. Okay? Right? Now the energy might change form from like potential to kinetic. That's okay. Okay. But guys, if this right here is like 135 joules, then this is also 135 joules. So the quantity of energy stays the same. Now, if you have an open system, then you can add or subtract energy to the system. Now, the energy has to come from somewhere. It's not being created whole cloth, right? But there could be work done on or by the system. That's why plus or minus work. Okay. All right, so you guys go with closed and open systems? Because we're going to do some examples. All right, you guys ready for some examples? Okay. All right, I have a closed system right here. Here's Galileo dropping balls off the tower. So the question might be something like, what's the crash speed? Like how fast is the ball crashing into the ground? Now there's an old way to do it and a new way to do it. The old way, you could have done this like 2 months ago. You guys remember kinematic formulas? You could use the third one down here and solve it that way. Okay. But there's a new way to think about it. And that's in terms of energy conservation. It's what type of energy at the very top? Yeah, MGH, potential energy. And it got there by Galileo was lugging that ball up in the first place. All the way up the stairs with force mg, height h, gave it some mgh. Okay. When this ball is just about to crash down into the ground, it has all what type of energy? Kinetic. Because if this is like 505 joules at the top, is it 505 joules at the bottom? Yep. So you can say this. Sum of energy at the top equals sum of energy at the bottom. Mgh at the top equals 1/2 mv squared at the bottom. The mass cancels. Here's the crash speed every time, square root TGH. You guys saw that back in kinematic days. You're seeing it now. Next semester, when we do Bernoulli principle, you'll see it again. You see that all over the place in physics. Okay? As long as he doesn't throw it, as long as he just drops it, square root TGH. Okay? You guys got square root TGH? Okay. It's an old way to do it. It's a new way to do it. Okay. This poster is really similar. It just turns it around backwards. What if you took the ball straight up into there? How high can you throw the ball if you know your throw speed? Or if you know how high it goes, how fast did you throw it? That's this little equation right here at the bottom. Okay? Right. Now, here's 2 ways to do it. Here's the old way, kinematic. You can solve it, bing, get an answer. Or this answer, bing, you ask that question. Okay? Here's the new way. And it looks just like Galileo, except backwards. It's all kinetic at the bottom, all potential at the top. And if you solve for either how high does it go, bing, or how fast did you throw it, bing. And look, speed is square root 2gh. There it is. It's showing up all over again. Old way, new way. It's a match. Here's the old way. Here's the new way. They look totally different, except the answers are the same. Whoa. Physics wins again. All right. So you guys can throw a ball in there? In here? Oh, you guys know a question I like to ask is, how about this? Suppose you got 2 friends, and one friend can throw 3 times as fast as the other friend. Guys, if you can throw 3 times as fast, how many times higher can you throw? 9 times. So 3 times as fast squared, that's like 9 times the height. That's a good question, right? Think it's been a quiz question? All right, next one, block spring earth system. So, okay, there's no friction, So I'm not including the track. Now there is a force from the track, but it's only a what kind of force? No. Normal force. And since the block is sliding perpendicular to that, the normal force never does any work on the block. Okay, that's a little side thought, right? So I got a block spring earth system. Okay. When I press that block into the spring, where is all the energy? Spring potential? Yeah. And what's the formula for that? 1/2 kx squared. That's right. Then I need to pick some final location. I'm going to pick this point at the top of the loop. So I got point A and point B, initial to final. You pick any point as the final. Okay. Maybe I have a question like, no, I wonder how fast it's going at the top or something like that. Right. Well, in terms of energy, guess what type of energy does this have at the top? Has what and what? Yeah, gravitational potential, because it had to climb that height against a gravity field. And it better also be in motion, make it around the loop. So it better have some kinetic also. So it's got both, right? Let's do a numerical example. Suppose it took me 100 joules of energy to squash that spring. So now I got 100 joules of spring potential energy, 1/2 kx squared. It's 100 joules. And then let it go. Pew! Suppose it takes 30 joules, 30 joules to lift up to this height. How many joules of energy are left over for its motion? 70. Because 100 equals 30 plus 70, right? The next step could be, if I told you the mass, could you solve for the speed? You could do that. Right, you guys can do that? All right. All right. Ooh, look who is back. It's the Atwood. Right. But now we're going to think about this a little bit differently. Right? So kind of start from the endpoint. The endpoint, the question you normally get in this chapter with the Atwood is, how fast is it moving after some distance moved? You guys see I have a distance moved h, right? And the question could be like, how fast is it moving? Again, there's two ways you could solve this. The old way of solving it is, okay, well, I could go through dynamics. I could solve for the acceleration because you know how to do that. We did that earlier today. And then you kick over to kinematic motion and pull out one of those equations. Okay, now they know the acceleration, how fast it's moving after some distance. That sounds a lot like, get my kinematic equations. That sounds a lot like this third kinematic equation. I know acceleration, know how far it moved, want to say how fast it's going, right? You could do it that way. It would take a lot of paper. It would take a lot of time. There's a faster way to answer that question. And that faster way is hidden underneath this paper right here. We're going to go M1, M2 are a system, conservation of energy. All right, you guys ready to figure out how to solve this? All right. You guys tell me, what's sort of the source of energy? Like, where's all the energy coming from? So suppose it starts at rest. So it starts right here. Is that rest? At rest, does it have any kinetic? No, I don't see any springs. But it will change height. That sounds like what kind of energy? MGH, right? MGH potential. In fact, which block is falling down? The big block, the M2. Yeah, the big block. Right. So that's sort of, you think of that like the supply of energy. The fact that the large block is falling, that's supplying energy for the system to move. Right? Now that energy is going to go to 3 different places. You got something plus something plus something. Right? What's one place where that energy goes? It goes into doing what? Does it have to lift the small block? Right? It has to lift the small block the same height that the large block fell. Right? So the large block falling lifts the small block. This H is this H. I mean, one's going down, one's going up. Right? Also, where else does the energy go? Kinetic, right? At the end of that motion, well, the blocks are moving. Right? They're not done moving. We just kind of arbitrarily cut it off for some distance move, right? But they're still in motion, right? So they each have their own 1/2 mv squared, right? Now, guys, is this V, are they the same speed? Yeah, because they're tied in the same string. So it's the same height H, the same speed V. That's why I didn't put any subscripts on the H or the V, because you don't need subscripts, it's the same, right? They're probably different masses though, right? So M1 and M2 are different. So yeah, if I gave you some mass values and a height change, you could very quickly solve for the speed, right? That's the classic Atwood question you get in an energy chapter in physics. We said again, is how fast is it moving? You solve for the speed. after some height change, h, right? Notice what I never had to solve for. I completely skipped through. I never solved for the acceleration of the system. That's nowhere on this page. I never solved for any time intervals. I don't see anything about time up here. We just zip, 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 just skip straight through that and cut straight to the answer. Okay, that's it. All right. I never solved for tension and string. Right, it's not on here either. All right. Here's a more complicated version. I've had 3 blocks, and I got this block falling. It's going to lift this block, and maybe I'll even throw a friction in the mix. Wow, got a lot going on. So I'll think about this being like an open system. So the large block falling is supplying the energy. If there's a friction force up here, times this distance, I have to subtract out the work done by friction. And whatever I'm left over with does 4 things. Has to lift the small block, give each of these 1, 2, 3 blocks its own speed. So that's 1, 2, 3 different kinetic energies. Okay, a little more complicated. You guys can navigate that. Okay. All right. Pendulum speed. Show you guys your lab table on this one. Okay. You guys had a lab, and you had a speed gate down here, and go through the speed gate, and you reported what was the speed, and you compared that to the calculated value that we're about to go through right now. Like, how do you calculate how fast should it go? And you guys said, oh, it looks the same all the way down, regardless of the angle and the length, the equation for the speed and the measurement of the speed, they match. So let's start with energy conservation. There's my energy conservation. Guys, what type of energy right here? Potential energy, MGH. What type of energy right here? 1/2 mv squared. Hey, does that sound a lot like Galileo dropping balls off the tower? I think it does. In fact, we're trying to solve for the speed at the bottom. Same idea too. Right. Again, the direction of the speed doesn't matter. Yes. Scalar quantities. That's all good. Okay. In fact, it kind of is the same. But there's one last twist. And the one last twist is a little bit of geometry. We got to figure out what is this height change based on this L and this theta. You guys ready to do that? Okay. You guys see a nice right triangle right here? Right triangle. Is this leg of this triangle L cosine theta? L cosine theta? Okay. And this L is this L. It's all the same length L. So the height change, therefore, is the full L minus the L cosine theta. Here's the rest of it right here. That makes sense, right? The full L minus the L cosine theta is the height change. If you like, you can factor out the L if you want to. All right. So the answer, the speed at the bottom is the square root of 2gh, except where the h goes, I'm going to put this expression right here. You guys see that? All right, that's it. That's exactly what you guys did on your lab not too long back. All right, one last little detail. What if you gave this a push? Now, if you give it a push, what kind of energy does it also have at the top? Kinetic, 1/2 mv squared, which I put in gray, so you can easily ignore it, because you normally don't get that. But if you did, it would be there. And how does that enter into the end? I obviously skipped a few algebra steps, right? But here's what it is, and here's what it does not at the end. What it is, the actual answer is square root of the push speed squared plus, and then 2gh. What it is not, that a lot of students miss, it is not the push speed plus, and then square root of 2gh. That would give you the wrong answer. The correct answer ends up being square root of push speed squared plus 2gh. And you can get that by doing all the algebra steps between here and here. That is good. Okay. All right. Pendulum speed. Don't skip. Ooh, car brakes to a stop. Right. The classic question could be, what's the braking distance? And there's some variations on that question. But there's an old way and a new way. The old way is you figure out the acceleration of the car, which we did yesterday. You guys remember that was just coefficient of friction times gravity field? That's your notes from yesterday. And then you can go back to kinematic and figure out the braking distance. But there's an easier way with an open system through energy. Guess what type of energy does the car have at the beginning? Kinetic, 1/2 mv squared. What kind at the very end when it's stopped? Or how much does it have at the end? 0. And where'd the energy go? Work done by friction. So I'm going to subtract that off. That's why it's an open system. So 1/2 mv squared minus force of friction times distance goes to 0. Right? There's no hills. That's why there's no MGH, nothing like that. All right. All right. Show you guys the rest of this. So here, I may have skipped a couple of algebra steps, but here always ends up being the answer. And a really classic set of questions comes from, what's the relationship between initial speed and braking distance? It's a squared relationship. right? So for example, if the car was going 3 times as fast, that would be how many times the braking distance? Okay, it's 3 times as fast. What's 3 squared? 9, so it would be 9 times the braking distance. Here's a related question. I think I may have asked this the other day, I forget. Right. Suppose I have a big old gas hog, I got a big old vehicle, and I would go from 0 to 20 meters per second. It takes me 1 gallon of gasoline, and I'm burning this like Captain Pollution or something. So it takes a whole gallon to go to 20 meters per second. Right. Now I'm gonna brake the car, so now it's stopped. Right. Now I'm gonna get up to 60 meters per second. Guys, is that 3 times the speed? Yeah, right. How many gallons of gasoline does it take to get to 3 times the speed? 9 times the energy. That's 9 times the gallons of gasoline. It's 9 gallons. Right? Because 1/2 mv squared, 3 times the speed, that's 9 times the energy. All right. What else we got here? Ooh, this one's a little bit more involved than anything tomorrow, but this one's a good one to know. What's the minimum height for a roller coaster to get around the loop? This is always the answer. If you take physics in college, they're going to ask you the question. Pull this out, got the answer, boom. More college points. Ooh, powerlifting an elevator. So let's go through step by step. You guys know power is work over time. Talked about that earlier today. Because work is equal to what times what? Force times distance, right? Now, one last detail here. Guys, what is this right here? What is distance over time? Velocity. There you go. So do you guys think there's a motor at the top of this elevator shaft pulling, drawing some watts of power to pull up that elevator? Yeah, right? How many watts of power? Well, if you know the tension force in this cable, you know how fast it's being pulled up, well, you just multiply it. That's it. That's how many watts of power. That's a fun one, right? Guess not? All right. All right. We're going in for the end right here. All right, here's the last few posters. They're all mechanical advantage. Is this the last lab you guys did? Okay. Now, guys, in a mechanical advantage, if you get a mechanical advantage, say with a pulley system, can you sort of increase your strength to pick up something really heavy that you couldn't pick up before? Yeah. Right. So here I'm looking at 3 to 1, 3 times as strong. Okay. Can you increase the amount of energy in the system? No. Right. So work input could at best be work output could at best be work input. It's 100% efficient. Right. So we still got conservation of energy. Right. But you can amplify your strength, but not the amount of energy. Right. So mechanical advantage. Here's your lab table. You guys did a little 1 to 1, 2 to 1, 3 to 1, 4 to 1 mechanical advantage. You guys did all those. Okay. Here's a different way to get a mechanical advantage. Okay, with wheels. Here's a mechanical advantage with an incline. Okay. Here's a whole list of simple machines. Get a mechanical advantage from any of those. All right, and that is a wrap on the review. All right, you guys are all ready for tomorrow.